A white egg sits in a wine glass under a block of iron heavy enough to flatten bone in an instant. Men step back. Steam leaks from valves overhead. The floor is already humming before the blow arrives. Then the hammer drops, hard enough to shake the building, precise enough to split the shell and leave the glass standing. That trick was not a circus stunt. It was a sales pitch for one of the most important machines heavy industry ever built, a machine that taught metalworks how to deliver gigantic force without surrendering control. Before it, there were parts the industrial world wanted and could sketch and finance and pray over, but still could not reliably make. After it, the limits moved. Ship shafts grew. Railways spread. Guns thickened. Iron became steel, steel became infrastructure, and whole nations started measuring their future in forgings. The problem began before the famous demonstration, before the patent, before the arguments over credit. It began with size. Early forge hammers were brutal but clumsy. A tilt hammer, driven by water wheel or steam, could pound out bars and smaller pieces, but it had a built-in weakness. The bigger the workpiece on the anvil, the less room the hammer had to fall. The work that needed the heaviest strike got the shortest drop. The force ran out exactly where industry needed it most. By the late 1830s, that weakness had become expensive. Steam engines were growing larger. Marine engines wanted thicker shafts. Locomotives wanted stronger crank parts and axles. Foundries could cast large masses, but casting was only the beginning. Cast metal often carried internal defects, uneven structure, trapped cinder and wrought iron, weaknesses that had to be beaten out, welded tight, drawn into shape. A giant shaft was not just a big piece of metal. It was a test of whether force could be applied deep enough, evenly enough, often enough, to make that metal trustworthy. Into that bottleneck stepped James Nasmyth, the Scottish engineer who had moved to Manchester in 1834 and opened the Bridgewater foundry at Patricroft in 1836. He was not yet a legend. He was a talented mechanic with a growing business and a habit of thinking in machine geometry. Then came the job that exposed the gap in the whole system. During the building of the Great Britain, the engineer Francis Humphreys needed a forge hammer powerful enough to make the vessel's immense paddle shaft, about 30 inches in diameter. England and Scotland, the heartland of industrial ironworking, did not have one. That was the personal stake at first. One engineer needed one tool for one impossible piece. Nasmyth's answer, proposed in 1839, was severe in its simplicity. Put the hammer block, the tup, directly under a vertical steam cylinder. Attach piston to tup. Lift the mass by steam. Then let it descend straight down onto an anvil holding the heated work. No awkward tilt. No wasted motion. No dependence on the shape of the piece for swing clearance. The hammer could rise higher, fall truer, and strike with repeatable force. What good was more power if it landed blindly? Under the noise, the idea was elegant. Steam was not just a source of motion. It was a means of control. By adjusting the valve gear, the operator could change the height of lift, the speed of repetition, the violence of the blow. Early versions were free-fall machines, lifted by steam and dropped mainly by gravity. Later improvements increased control and rate. In 1847, Nasmyth patented a self-acting improvement that let the hammer regulate its own cycle more effectively, reducing delays and helping the machine deliver faster, more consistent work. Industry did not wait politely for patents to settle. In France, at Le Creuset, François Bourdon and the Schneider Works were moving toward the same idea, and the dispute over who truly invented the steam hammer never stopped being sour. Nasmyth became the name history remembered. Bourdon built the first working example before Nasmyth's own patent was secured in June 1842. The machine was already bigger than any one man's memory of it. That matters, because the steam hammer was born inside an age that was beginning to reward publicity almost as much as engineering. The first hammer based on Nasmyth's design was completed in 1843. By then the Great Britain had been altered from paddle wheels to screw propulsion, so the exact job that had inspired the machine had changed under its feet. It did not matter. The need remained. There were shafts to forge, anchors, railway components, tools, heavy rods, later steel masses that would have mocked older hammers. Nasmyth understood something else too. A new machine does not conquer industry by existing. It conquers by being seen. So he showed it off. That is how the egg ended up under the hammer. At one end of its range, the machine could make a building shudder. At the other, it could descend lightly enough to crack only the top of an egg in a wine glass. The point was not delicacy for its own sake. The point was that power and precision had been fused in one frame. A forge no longer had to choose between a tap and a smash with different tools. One hammer could do both. In the forge, that changed everything. A white-hot puddled bloom or steel ingot came from the furnace at roughly 1,200 degrees Celsius, glaring, shedding scale, soft enough to move but not soft enough to forgive hesitation. The hammer lifted. The work was turned. The dies met the metal again. Each blow compacted, spread, drew out, and shaped. In wrought iron, the repeated strikes helped consolidate the fibrous mass and squeeze cinder from where it did not belong. In steel, especially as ingots grew larger later in the century, forging helped break down the cast structure, closing voids and forcing the metal toward the dimensions needed for shafts, axles, rolls, connecting rods, gun components. There was no calm classroom version of this process. It happened amid deadlines, heat, and the constant risk of error. A mistimed lift, a slip in the tongs, scale flying from the surface, a workpiece turned too slowly under the top, and the same machine that had just demonstrated finesse could take a hand, crush a foot, throw metal where flesh happened to be standing. It was ingenious. It was also brutal on the men beside it. That was the hidden bargain. Power moved from gangs of strikers into a machine frame, but danger did not vanish. It concentrated. Forge workers still had to guide the piece, read color, judge temperature, coordinate timing, live beside impact and radiant heat for entire shifts. They worked near iron hot enough to blind with glare, and near moving masses measured in tons. No soft language belongs there. That is one of the cruelest bargains in industrial history. And yet the machine spread because it solved the real industrial arithmetic. It made forging cheaper, faster, more uniform, more scalable. Between 1843 and 1856, Nasmyth's foundry produced 493 steam hammers. That number alone tells the story. This was not a curiosity built once and admired forever. It was a system being copied into the bones of manufacturing. Some hammers could deliver as many as 220 blows per minute. Some small examples could work on fine pieces. One Royal Mint hammer was used for machinery and tool maintenance rather than giant marine shafts. At the other end of the range, steam hammers grew over 35 feet tall and weighed around 90 tons. The machine scaled with industry because industry kept asking for heavier forgings. Bridges demanded better iron. Railways demanded tougher axles and rails and wheel parts. Shipyards demanded larger marine hardware. Arsenals demanded reliable heavy forgings because failure in a workshop became failure in the field. The stakes moved outward. A bad shaft in one shipyard was a financial loss. A nation unable to forge large, trustworthy components at scale had a deeper problem. It meant slower shipbuilding, weaker artillery programs, less confidence in railway expansion, more dependence on outside suppliers. Once steam hammers proved they could be built, run, and sold, they became part of national capability. The machine was no longer serving one engineer's headache. It was serving fleets, rail systems, state mints, naval dockyards, weapons plants, and every private works hoping to win contracts from them. By 1861, the Krupp works at Essen had raised the stakes again with the 50-ton hammer known as Fritz. That single number, 50 tons, explains why the steam hammer's story belongs in steel history and not just mechanical history. A hammer that size was not about convenience. It was about the ability to take increasingly massive hot metal and force it, step by step, into forms required by industrial power. Germany's heavy industry was climbing. So were the expectations placed on forged parts. If a works could handle bigger ingots and heavier pieces, it could compete for the contracts that mattered most. The machine itself became the protagonist of the age because every expansion of its size pulled another industry upward with it. Then steel output began to surge. The Bessemer process, patented in 1856, and later open hearth production changed the scale at which steel could be made. But producing more steel did not erase the forging problem. In some ways it sharpened it. Bigger steel ingots still had to be worked into shafts, rings, armor components, gun parts, and structural pieces with dependable internal integrity. A furnace could make a mass of metal. It took a forge to persuade that mass into service. That is why the late-century giant hammers matter so much. At Le Creuset, the Schneider Works erected the Creuset steam hammer in 1876, completed in 1877, a machine that displaced Fritz as the most powerful in the world. Depending on the dies fitted, its striking capacity was given between 75 and 100 tons. Its steam cylinder, stacked as two cylinders, stood 19 feet 8 inches high with an internal diameter of 6 feet 3 inches. Steam at about 71 pounds per square inch lifted the system. The piston could travel 16.5 feet. The actual force delivered could reach roughly 3,300,000 foot-pounds. Beneath it sat an anvil block of 750 tons. Numbers like that stop sounding like workshop language and start sounding like geography. To keep such a machine useful, the forge around it had to evolve as well. Bigger furnaces. Better cranes. Heavier handling gear. More planning before the heat. When an enormous steel piece came out, there was only so long before temperature dropped and resistance climbed. The hammer operator, the crane crew, the men on the floor, all of them had to read one another without delay. The hot ingot came out the color of a small sunrise. Then the hammer started its work, and every second cost money. This is where the civilizational stake finally appears. Modern life rests on parts that are boring only after someone else has made them dependable. Main shafts for marine engines. Forged axles that do not snap under load. Steel components for bridges that carry lives instead of ending them. Artillery and armor, for better and worse. Later, turbine rotors, heavy crankshafts, landing gear components, massive rings for pressure vessels. The steam hammer did not make all of those in final form, and it was eventually outclassed in the biggest jobs by hydraulic forging presses. But it taught industry the governing lesson: concentrated force, applied controllably, could turn giant metal masses into trustworthy components. That lesson changed business as much as mechanics. Once one works proved it could forge larger pieces, rivals had to answer. Capital followed capability. Firms that could invest in heavier forging equipment moved up the contract ladder. Firms that could not were left doing smaller work, less profitable work, replaceable work. The steam hammer was a machine, but also a sorting device for industrial capitalism. It sorted men too. Skilled hammer operators mattered. So did the crews who handled the hot work. But the more impressive the machine became in public imagination, the easier it was to overlook the labor standing inches from the dies. Crowds remembered the egg in the glass. The men in the forge remembered the heat, the noise, and the need to get one more turn before the next blow landed. History likes demonstrations. Industry runs on exposure time, body position, and whether the signal was understood fast enough. By the turn of the century, steam hammers were no longer the final word in heavy forging. Hydraulic presses offered a slower, steadier squeeze better suited to some enormous steel work. Air hammers and mechanical hammers took over other jobs. The age of giant steam impact had competition. But replacement is not the same as irrelevance. Steam hammers remained useful in many works because repeated impact was still exactly what many forging operations required. They were cheaper in some cases, faster in others, familiar to shops that had built whole routines around them. And the idea never died. It just changed body. Today, in modern forges, whether the tool above the work is steam-powered, air-driven, hydraulic, or fully automated, the principle is the same principle that made that first vertical hammer so important: lift force, guide it, deliver it exactly where the metal can still move, and repeat until the part is no longer a hopeful casting but a component with a job. The names on the machines changed. The physics did not. That is why the old steam hammer still matters to steel history. Steel is often told as a furnace story, a chemistry story, a story of carbon percentages and converters and open hearth roofs. It is those things. But steel only becomes civilization after it is made into parts that survive service. The hammer lived in that gap between molten possibility and usable strength. Even the famous egg demonstration feels different once that is understood. It was not really about finesse. It was about trust. Trust that a force large enough to work the metal of engines, ships, rails, guns, and later the heavier hardware of the steel world could also be governed by a human hand at a valve. A machine that violent, under control, becomes manufacturing. Out of control, it is only impact. That old bargain still sits inside the metal world around us. The bridge overhead. The rail under a freight train. The forged shaft inside a power plant. The landing gear that hits the runway harder than it looks. Their lineage runs back through presses and hammers, through furnace doors and forge floors, through the moment industry learned to strike in a straight line and mean it. If this one changed how you see the metal hidden inside modern life, stay with the channel and drop the next industrial machine you want dissected in the comments.